I'm Philip Leday.
I'm Matthew Hale.
And I'm Will Lyles.
We're going to be discussing the importance of decline curve analysis and why it is relevant to reservoir dynamics. Decline curve analysis is important to reservoir dynamics because it is a graphical procedure that is used routinely by engineers to estimate recoverable hydrocarbons in place, hydrocarbon reserves at abandonment conditions, forecasting future oil and gas production rates, and to forecast the life of a well. A few conditions that can affect the rate of decline of a well are separator pressure, tubing size, choke position, workovers, compression, and operating hours. As long as these conditions do not change, the trend in decline can be analyzed and extrapolated to forecast future well performance.
Developed by J.J. Arps in the mid-1940s, it is one of the first methods used for decline curve analysis. The three types of curves Arps used to best fit data and predict flow rate versus time are exponential, hyperbolic, and harmonic curves. Each of these types of curves are used in different situations as talked about in the following slides. Arps decline curves plotted on a flow rate versus time graph only predict the well in the depletion phase. They do not show the well when it is in laminar flow. A graph plotting these three types of curves is shown on this slide to give a visual representation on how they are shaped.
Instantaneous, or current decline rate, is known as the base equation for all decline curve analysis. In this equation, D is equal to the fractional change in rate over the change in time. This value is typically expressed in percent per year. The graph below gives a visible representation of instantaneous decline, where D is equal to the slope over the rate. The exponential decline curve occurs when the decline rate D is constant. If D varies, it is considered either hyperbolic or harmonic. Mathematically, the exponential decline curve is equivalent to a straight line on a log of production rate versus time plot. The exponential decline curve is also known as the constant percentage decline curve. In this equation, we see that D is the decline rate percentage, and it remains constant. Due to the linear trend of exponential decline, it is known as the most recognizable type of decline curve. In figure B2, we see two graphs plotting flow rate versus time. The graph on the left is replotted on the right, and the vertical scale is changed from flow rate to log flow rate. In both cases, we see that D is constant. However, the graph on the right displays the linear nature of an exponential decline curve when it is plotted as log flow rate versus time rather than flow rate versus time. When production follows an exponential decline, two different methods can be used to calculate rate forecasts. The nominal decline rate is more suited for tabular data, while the exponential model is used more appropriately for a graphical approach. In equation B3, we see that the nominal decline uses a lowercase d, representing an approximation of the slope, and a q subscript 1, representing a preceding rate. In equation B4, for exponential decline, we see it uses a big D for the actual slope and a Q representing an instantaneous rate. In figure B3, we see the difference between nominal and exponential decline. As seen, uppercase D is related to the slope of the line, whereas lowercase d is derived from the segment which approximates that slope. In addition, we see the rate by which the slope is divided is different. In one case, it is the instantaneous rate, q. In the other case, it is the preceding rate, denoted by q subscript 1. The difference between lowercase d and uppercase d is usually very small and is often within the proper accuracy of the data. So even if misapplied, the error is not substantial between nominal decline and exponential decline.
A second type of decline model that we'll look at is the hyperbolic model, which happens to be the most common type. It is often observed in unconventional shale gas formations. The hyperbolic decline model differs from the exponential model in that the constant b falls between 0 and 1. This is the flow rate equation using the hyperbolic decline model, where d sub I is initial decline at time t equal to 0. The hyperbolic model also differs from the exponential model in that neither the slope of the curve nor the decline rate remain constant. This is what the hyperbolic decline curve looks like as a Cartesian plot. Notice that d is not constant here. And here's what it looks like as a semilog plot. Notice slope is not constant here. A problem that often arises when using the hyperbolic model is that over long periods of time it can overestimate reserves. To solve this problem, the hyperbolic curve is converted into an exponential decline at some predetermined point in time, as shown in the graph below. For example, the decline rate may start out at, say, 30% and continue to decline in a hyperbolic fashion until the decline rate reaches, say, 10%, at which point it will begin to decline in an exponential manner. This modification allows for a more accurate estimate of remaining reserves. The hyperbolic equation was also modified to include this transition from hyperbolic to exponential, as noted below.
The last of the three types of ARP's decline curves is harmonic. It is the least used of the three types of curves as it can only be used on certain wells. A harmonic curve is a type of hyperbolic curve, but instead a b value of 1 is used. This b value makes the decline rate proportional to the flow rate. Some useful equations are shown on the slide, such as rate time, rate cumulative, and estimated ultimate recovery. Harmonic decline curves are the least used among the three types of ARP's curves because the conditions in which it can be used are less common. Some types of wells that harmonic curves can be used on are wells with effective recovery mechanisms, such as wells with gravity drainage. Harmonic curve is also a good fit in production of high viscosity oil wells driven by edge water. In the flow rate versus time plot, the lower part of the curve becomes flat and shows almost no decline or slope change. This means that recoverable reserves at a zero flow rate cannot be determined from the graph. Over the years, other methods have been developed that take into account different problems in ARP's decline curves. A main problem with ARPS is that it is only applicable during the depletion period of a well when the well is in a boundary-dominated flow. ARPS cannot be used when the well is in transient flow. Fekovich used the flow equations to develop tight curves for transient flow, which was combined with ARP's decline curves for boundary-dominated flows. With this being done, it shows the entire production life of a well instead of just the depletion period. This graph shows the transient flow in the beginning stages of a well as plotted by the Fekovich method, and the boundary-dominated flow as plotted by the ARP's decline curves.
Now we'll look at a brief study that was published in the American Oil and Gas Reporter in 2011 that compared decline rates in various shale plays throughout the United States. In the study, production data was obtained from 1,885 horizontal shale gas wells, of which there were 838 wells from the Barnett Shale play, 467 wells from the Fayetteville Shale play, 305 wells from the Woodford Shale play, and 275 wells from the Haynesville Shale play. The data obtained from each well was then shifted so that they all had identical start dates. ARP's equation was used to develop decline curves for the wells. Average daily production was then plotted against time on a year-by-year basis to show the changes in average production rates throughout the years. All of the wells in the study retained a B-value between 0 and 1, making them all hyperbolically declining wells.
Remarkably, production profiles remained similar in the Barnett Shale from 2003 to 2009, even though there were advances in stimulation methods and the average number of frac stages increased.
In the Fayetteville Shale, year-on-year improvement in production rates is evident. This is likely due to the increase in lateral length of horizontal wells and an increase in the number of stages fracked per well. Throughout the time covered in this study, production volume nearly doubled per well.
In the Woodford Shale, similar increases were observed, but the results were not quite as drastic as in the Fayetteville Shale. Even in the Haynesville Shale, a reasonable increase in production was observed from 2008 to 2009 due to improvements made in stimulation methods.
As you can see, these methods play an important role in reservoir engineering. They give us valuable information on the production outlook of a well. These methods also play an important role in economic decisions that are made. This information will also help in drilling future wells. Thank you for watching our presentation.